This paper presents an efficient algorithm for constructing a minimum size motion graph from a large motion capture database while satisfying user-specified requirements. As motion capture databases grow larger, they provide us with a richer variety of human motions and the ability to construct more powerful and higher quality motion graphs. However, it is very difficult to manually select a set of motions that result in a good quality motion graph. Motivated by making motion synthesis accessible to naive users, we present an algorithm for selecting such motions automatically. We cast the motion selection problem as a search for the minimum size subgraph from a large motion graph. We first compute a motion graph from the large motion capture database. A user selects a few motion segments that are required by her application. The user also specifies a set of requirements that reflect the application needs. For example, an upper bound on transition time between selected motions. Our approach then automatically finds additional motions in the motion database that result in good connectivity between the user-selected motions and keeps the size of the motion graph as small as possible. Our algorithm can scale to very large motion databases. In our experiments, we build a large motion graph from over 86,000 motion capture frames sampled at 30 Hz. Experiments show that our algorithm consistently generates subgraphs with small graph sizes while satisfying all of the user requirements. We now analyze the performance of our subgraphs for an interactive control application. We use value iteration to learn a good control policy. Our subgraph produces smooth motions that are responsive to user inputs. We compare our subgraph to a motion graph carefully crafted by an expert. Our subgraph is much smaller in size but achieves comparable motion quality and motion responsiveness. The value iteration table computed based on our subgraph is 10 times faster to compute and takes 4 times less memory to store. We also compare our subgraph to the best motion graph created by a novice user. With a similar graph size, the policy learned from this manually created motion graph lacks responsiveness and is not able to transition to the ducking behavior. Finally, we color code the animation. Green frames are the user-selected frames, purple frames are the additional frames our algorithm finds to connect the user-selected frames. They provide good connections between multiple behaviors. Our subgraphs are also well suited for offline motion synthesis. Its small graph size and guaranteed transition time between frames allow the search to converge to a good solution efficiently. Here we show an example motion generated using multiple behaviors in order to navigate through an environment without colliding with obstacles. The computation time was within seconds for an approximately 12-second long motion. The same algorithm did not converge to a feasible solution when searching the motion graph created by our expert because the search ran out of memory. It was also unable to find a valid solution when searching the motion graph created by a novice user due to its poor connectivity and responsiveness. Finally, we performed a user study evaluating the difficulty of manual motion graph construction. Our subjects confirmed that manually selecting a good set of motions for a specific task was difficult. We construct our subgraph under the same conditions as in the user study. The results of our user study clearly illustrates that in addition to being fully automatic, our algorithm outperforms manually constructed motion graphs across all of the metrics we have measured: construction time, average transition times, the size of the generated motion graphs, and measures of connectivity and user requirement satisfaction.